In this video, we will be talking about average atomic mass and some calculations that we can do with regard to average atomic mass. So first, we'll talk about atomic mass, and note that this is different from the mass number. Okay, they are different values. Atomic mass is defined as the mass of a single atom of an element. However, atoms are too small to measure their individual mass in grams. Therefore, chemists use relative masses. So the relative atomic mass is the mass of any atom compared with an atomic mass standard. And the atomic mass standard is the mass of one atom of carbon-12, which has been assigned a mass of 12.00 U. So that U stands for the atomic mass unit. And it's a unit of mass defined as 1/12 of the mass of a carbon-12 atom. So all of the atomic masses are relative to carbon-12. When you have an element in nature, it is generally a mixture of two or more isotopes. So recall that isotopes are versions of an element that have different numbers of neutrons. So the relative atomic mass for an element is an average of the masses of all the isotopes that exist. And this average atomic mass can be found on the periodic table. So this is a section of the periodic table for copper, and the average atomic mass is found at the bottom. So that number tells us that the relative atomic mass of copper is 63.55 U, atomic mass units. We also need to talk about something called isotopic abundance. So if we're going to do some calculations with average atomic mass, we're going to need two pieces of information. One is the relative atomic mass of each isotope, and the second is the isotopic abundance. So what is that? So that's the amount of a given isotope that exists in nature, expressed as a percentage of the total amount of the element. So how do we calculate average atomic mass? So the formula is that average atomic mass is going to equal the relative atomic mass of the first isotope, isotope A, multiplied by the abundance of that isotope. And then we add to that the relative atomic mass of the next isotope, multiplied by the abundance of that isotope. And we add to that the relative atomic mass of the next isotope times the abundance of that isotope. And we just keep adding those together for however many isotopes there are. And there's usually 2, 3, sometimes 4 or 5, but not any more than that. When you're using this formula, you need to make sure that the abundance is expressed as a decimal. Right? So you take that percentage, divide by 100 to get it to a decimal. Otherwise, your answer is going to be off by a factor of 100. So let's look at some samples. So the first one, natural chlorine contains two isotopes, chlorine-35 and chlorine-37. Calculate the average atomic mass of chlorine to 2 decimal places. So we're going to need some information. We've got the two isotopes, we need their atomic mass, and we need their isotopic abundance. So for chlorine-35, its mass is 34.969, and its abundance is 75.77%. For chlorine-37, atomic mass 36.966, abundance 24.23%. So we're going to take our little formula. Average atomic mass is going to equal the mass of chlorine-35 times its abundance plus the mass of chlorine-37 times its abundance. And remember, those abundances have to be changed to decimals. Divide them by 100. So there we have the numbers put in, 34.969 U times 0.7577 plus 36.966 U times 0.2423. You put that in your calculator and you find that the average atomic mass of chlorine is 35.45. And you could check that that is reasonable or incorrect by looking on the periodic table, because under chlorine, that's the number you will find. Next sample problem. Gallium exists naturally as gallium-69 with a mass of 68.93 U and an isotopic abundance of 60.1%, and gallium-71 with a mass of 70.92 U. What is the average atomic mass of gallium to 2 decimal places? Okay, so we'll start with our formula. Average atomic mass is going to equal the mass of gallium-69 times its abundance plus the mass of gallium-71 times its abundance. So we put in the information that we have. We have the mass of gallium-69 and its abundance, and we have the mass of gallium-71. But what about its abundance? We weren't given that in the question. So the key here is the fact that all of the isotopic abundances need to add up to 100%, right? So, or 1 when it's in decimal form. So we just need to take the 60.1% and subtract it from 100. Okay, so there since we're working with decimals, 1 minus 0.601 will give us what's left, right? Whatever's not gallium-69 has to be gallium-71. So that gives us a 0.399 abundance for gallium-71. So when we do that calculation, we get an average atomic mass for gallium of 69.72 U. And one more sample. The average atomic mass of rubidium is 85.47 U. So the question is giving you that, and that would also be the number on the periodic table. So if the question didn't give you that information, you could look it up on the periodic table. Rubidium exists naturally as 72.2% rubidium-85 with a mass of 84.91 U, and the other isotope is rubidium-87. What is the atomic mass of rubidium-87 to 2 decimal places? So this one's a little bit different. We still start with that formula. Average atomic mass equals the mass of rubidium-85 times the abundance plus the mass of rubidium-87 times the abundance. So if we plug in the information that we have, we know the average atomic mass, we have the mass of rubidium-85 and its abundance, but we don't know the mass of rubidium-87. So I've just left that as a variable m. And then we can determine the abundance of rubidium-87 by subtracting 0.722 from 1. So doing some of those calculations, so I've multiplied the mass and abundance of rubidium-85, and I've subtracted the 1 minus 0.722 in the next line. And now it's an algebra problem. We're solving for m. So we're going to move the 61.305 to the other side and subtract. And then we need to isolate m, so we're going to divide by 0.278, and that will give us m. 86.92 U. And when you're doing calculations like this, it's also important to check that your answer makes sense, right? This is rubidium-87. Its mass should be close to 87. All of the masses should be close together, right? So if you end up getting an answer like 8,692, that doesn't make sense. You've probably forgotten to change your percentages to decimals, and you just need to divide by 100 to get to the correct answer. So make sure you check if the answer actually makes sense.